Now we are going to start the second module in our syllabus. Second module we symmetric key encryption അല്ലെങ്കിൽ cryptosystems ആണ് പഠിക്കുന്നത്. പ്രധാനമായിട്ട് ഇതിൽ നമ്മൾ പഠിക്കാൻ പോകുന്നത് DES ആണ്, but there are other concepts also which we are going to learn. So let's get into it. First section എന്ന് പറയുന്നത് നമ്മൾ already first module പലപ്പോഴായിട്ട് കണ്ടിട്ടുള്ളതാണ്. എന്താണ് symmetric key? This is symmetric key crypto system. What is the basic overview of symmetric key crypto system? നമ്മൾ നേരത്തെ കണ്ടായിരുന്നു എൻക്രിപ്ഷനും ഡീക്രിപ്ഷനും ഒരേ കീ സീക്രട്ട് കീ യൂസ് ചെയ്ത് ചെയ്യുന്നതിനാണ് സിമെട്രിക് encryption എന്ന് പറയുന്നത്. So there is a plain text and using some encryption algorithm, a particular secret key K is used to convert into the encrypted form of the plain text. So encryption using the key K and the plain text X will give you the ciphertext Y. This is sent to the receiver. Receiver ന്റെ കയ്യിലും ഇതേ same key ഉണ്ട്. So the decryption algorithm, which is going to reverse the encryption algorithm, will be done using the same key. എന്നിട്ട് ciphertext ന്ന് we will get the plain text. Okay, ഇതാണ് ബേസിക് ഓവർവ്യൂ. ഒരേ സെയിം കീ യൂസ് ചെയ്ത് എൻക്രിപ്ഷനും ഡീക്രിപ്ഷനും ചെയ്യുന്നതിനാണ് സിമെട്രിക് കീ ക്രിപ്റ്റോ സിസ്റ്റം എന്ന് പറയുന്നത്. Okay, and this is the model that is being used. There is a message or plain text X. It is given into the encryption algorithm, and there is a key source or a key generation which generates a key K, and that key is used to encrypt the message X to give the ciphertext Y, and the key is the same for decryption also. So the key has to be sent through a secure channel to the receiver. എന്നിട്ട് ആ കീയും കിട്ടിയ സിഫർ ടെക്സ്റ്റും കൂടെ ഡീക്രിപ്ഷൻ അൽഗോരിതത്തിൽ ഇട്ടിട്ടാണ് പ്ലെയിൻ ടെക്സ്റ്റ് തിരിച്ച് റിട്രീവ് ചെയ്യുന്നത്. ഓക്കെ, ഇനി ക്രിപ്റ്റനലിസ്റ്റ് എന്താ ചെയ്യാൻ നോക്കുന്നതെന്ന് വെച്ചാൽ they are trying to guess from the cipher text what the key is and what the plain text will be. Okay, ഇതാണ് ക്രിപ്റ്റനലിസ്റ്റ് ചെയ്യുന്നത്. Okay, now cryptography എന്ന് പറയുന്നത് is usually ഏത് ക്രിപ്റ്റോ സിസ്റ്റം എടുത്തു കഴിഞ്ഞാലും there are three characteristics for a crypto system. Okay, ഒന്ന്, it is the type of operation that is used for the transformation. So നേരത്തെ ഞാൻ പറഞ്ഞായിരുന്നു we learned ciphers, either substitution ciphers or transposition ciphers. Okay, and in the case നമ്മൾ ഇനി ഡെസും ബ്ലോക്ക് സിഫേഴ്സിന്റെ അടുത്ത് നോക്കുമ്പോൾ ഇതേ സബ്സ്റ്റിറ്റ്യൂഷനും ട്രാൻസ്പോസിഷനും ആൻഡ് കോമ്പിനേഷൻസ് ആർ കോൾഡ് കൺഫ്യൂഷൻ ആൻഡ് ഡിഫ്യൂഷൻ. കഴിഞ്ഞ ക്ലാസ്സിൽ നമ്മൾ ഡിസ്കസ് ചെയ്തതാണ്. Okay, so one dimension is the type of operation that is used for the transformation. അടുത്തത് is the number of keys. So ഒന്നെങ്കിൽ we have symmetric key or we have asymmetric key, അല്ലെങ്കിൽ a single key which is secret key, or two keys which is public key crypto system. Okay, so number of keys base ചെയ്ത് another characteristic of the system നമുക്ക് പറയാൻ പറ്റും. പിന്നെ the next thing is the way in which the plain text is processed. ഒന്നെങ്കിൽ സിംഗിൾ ബിറ്റ്സ് ഓർ ബൈറ്റ്സ് ആയിട്ട് നമുക്ക് എടുത്ത് പ്രോസസ് ചെയ്യാം, അല്ലെങ്കിൽ ബ്ലോക്സ് ഓഫ് ബൈറ്റ്സ് ആയിട്ട് എടുത്ത് പ്രോസസ് ചെയ്യാം. സോ ഇറ്റ് ഇസ് ഐദർ ബ്ലോക്ക് സിഫർ ഓർ സ്ട്രീം സിഫർ. ഈ മൂന്ന് ക്യാരക്ടറിസ്റ്റിക്സ് വെച്ചിട്ടാണ് ഒരു ക്രിപ്റ്റോ സിസ്റ്റത്തിനെ നമ്മൾ കാറ്റഗറൈസ് ചെയ്യുന്നത്. Okay, now this we have already seen what is a stream cipher and a block cipher. Stream cipher is if one byte at a time or one bit at a time is taken and the encryption is done, then it is called a stream cipher. So it is bit stream generator will be there. So the bits will be coming one by one, and taking that we will be doing the cipher. But in the case of block ciphers, it is a block of bits. So here B is the size of the number of bits. ഒരു ബ്ലോക്കിനെ എടുത്തിട്ടാണ് എൻക്രിപ്ഷനും ഡീക്രിപ്ഷനും ചെയ്യുന്നത്. Okay, now there are two types of mapping which can be done. One is reversible and the other is irreversible. Okay, reversible mapping എന്ന് വെച്ച് കഴിഞ്ഞാൽ ഒരു പർട്ടിക്കുലർ പ്ലെയിൻ ടെക്സ്റ്റ് എടുത്തു കഴിഞ്ഞാൽ ആ പ്ലെയിൻ ടെക്സ്റ്റിന് മാത്രമേ ഈ പർട്ടിക്കുലർ സിഫർ ടെക്സ്റ്റ് വരത്തുള്ളൂ. So you can see for if we are taking 2^2 എന്ന് പറഞ്ഞ് നമ്മൾ എടുക്കുകയാണെന്നുണ്ടെങ്കിൽ there is 2-bit data എടുക്കുകയാണെന്നുണ്ടെങ്കിൽ the ciphertext can be any of those 2 bits can replace this value. And this is reversible. If you see ciphertext 1, 1, we know that the plain text is 0, 0. Okay, and there cannot be an overlap. But irreversible mapping in the you can see the 1, 0, 1, 1 inum, the ciphertext is 0, 1, 0, 1. So now when you see the ciphertext 0, 1, you're not sure whether you should replace it with 1, 0 or with 1, 1. Okay, so this we can convert from plain text to ciphertext, but converting from ciphertext to plain text is not easy. Okay, so this is called a singular transformation, one-way transformation. So this is singular transformation. And in the reversible mapping, we know how to transform from plain text to ciphertext and from ciphertext to plain text. So this is a non-singular transformation. Okay, now before we go into the DES algorithm, we have already discussed and we know the basic structure of the Feistel cipher structure. Okay, so that is the structure that's going to be used for DES. Okay, before that, we are looking at, there is an S block in substitution block in the DES cipher. Okay, and this particular structure which is given over here is called the ideal block cipher. So you have got a 4-bit input. 4-bit input means you have got numbers represented from 0 to 15. Okay, and for each representation for the 4-bit input that is being given, there is a 4 to 16. This is a 4 to 16 decoder and this is a 4 to 16 decoder. Okay, and over here, 16 to 4 decoder, sorry. So the input is given as 4 bits and the output is also 4 bits. But inside over here, what is happening is the actual, substitution. And this is also called, it is creating confusion. Okay, diffusion and confusion. Expansion block is diffusion and the substitution block is confusion. Okay, so here, if you see this particular architecture, this is a hardwired, substitution block. So in the hardwired substitution block, the 0th bit is being connected to the 14th bit. 1 is connected to 4. So that particular group of, values are being given. So if you have 0 as input, the output that you're going to get is 14. If you have 1 as input, the output you're going to get is 4. If you have 2 as input, then the output that you're going to get is, see over here, 13. Okay, and so forth. And this is also called an n-bit to n-bit block substitution, here where the n is 4. So you have got input 4, the output will also be 4. Okay, now, even though it is called the encryption decryption table, see, according to that particular figure, you have I showed you already that if the input is plain text is 0, then the output is going to be 14. Right? For input 0, the output is going to be 14. Okay, so in this way, this table is created based on that. And for ciphertext will be the opposite. Whatever is the plain text over here, that will be the plain text, for 0, 0. So 1, 1, 1, 0 is the ciphertext. If you see over here, 1, 1, 1, 0 will be converted to 0, 0, 0, 0. Okay, now, this is the most general form. This which you saw is the most general form of a block cipher. And it can be used to define reversible mapping. So each 4-bit data will be mapped onto another 4-bit data. Okay. And from that 4-bit data, we can get the original data. So it is a reversible mapping between plain text and ciphertext. And the Feistel structure refers to this ideal block cipher because it allows for maximum number of possible encryption mappings from the plain text block. Okay, so if you take 4 bits, 2 raised to 4 number of mappings will be there. Okay, here there is a practical problem. Okay, in the ideal block cipher, when the size is small, when it is equal to, like we saw just now, n is equal to 4, it becomes a very simple mapping and it becomes just like the substitution ciphers with all the vulnerabilities of the substitution cipher. We know already from earlier classes that it is vulnerable. A substitution cipher, a simple substitution cipher is vulnerable to cryptanalysis and statistical analysis. Okay, so to solve this particular problem, the block sizes, instead of having 4-bit data or 5-bit data, things like the size of the block is sufficiently increased. When the size of the block is sufficiently large, then cryptanalysis becomes infeasible. Okay, so in general, for an n-bit ideal block cipher, the length of the key defined should be n into 2 raised to n. Okay, so if you are taking a 64-bit block, then the size of the key for it to be, resistant to statistical attacks must be 64 into 2 raised to 64 bits. So over here, it is approximately 2 raised to 70, which is equal to 1021 bits. So the key should at least be this much for it to be resistant to cryptanalysis. Okay, and because of all these problems, Feistel, instead of using just one substitution or one transposition, from the Feistel structure or Shannon's theory was used to create the Feistel structure in ciphers, which says that use multiple blocks of confusion and diffusion, multiple rounds of confusion and diffusion, so that the strength of the, cryptography or the encryption will be higher. Instead of increasing the key size, we can do it multiple times. And that is where this is the structure that is being used for DES. We've already discussed Feistel structure, so I'm not going to go again into Feistel structure. Now we are moving on to DES, Data Encryption Standard. Okay, so originally this standard was publicized in 1974. Okay, and it was developed as the international standard for encryption in 1977 by NIST. Originally designed by IBM with input from NSA, and now we, because of many different cryptanalysis methods, single DES is no longer in use. Instead, 3 DES, triple DES is what is used. Okay, so in the DES algorithm, we have a symmetric block cipher. Symmetric block cipher. So the same key is going to be used for both the encryption and the decryption. Okay, the key size is 56 bits, and the input and the output, the block size is going to be 64 bits each. Okay, the concept of DES is easily understandable with the simplified DES structure, which we are not going to look over here. And then it is, it can be incremented to study the actual DES algorithm, but we are going to go directly to the DES algorithm. So let's look at the DES algorithm, DES encryption algorithm. Okay, so you can see over here we have got, this is an input key. Okay, so 64-bit key and 64-bit plain text, and then there is a permutation that is used in the case of the 64-bit key, and in each round 56 bits of that particular key is used. We're going to look at this key generation algorithm separately, and we're going to look at the actual encryption section separately. This is the overall depiction of the DES algorithm. Okay, so you have as input a block of plain text, which is 64 bits, and a block of key, which is also 64 bits. Okay, so we look over here in the encryption side. Please look at my cursor in the encryption side on the left-hand side. Initially, there is a permutation, and this initial permutation, the plain text is first permuted and then given to the 16 rounds that is there in the DES algorithm. Each round is doing the same thing, okay, but a different section of the key or sub key. This 56, a different sub key, K1, K2 to K16 is given for each round. Okay, and then there is we saw the Feistel structure. We know that there is a 32-bit swap in the 64. Left side 32 bits and right side 32 bits is swapped. And then this initial permutation is inversed over here. Okay, so now from this itself, you know that there is an initial permutation and inverse of the permutation. And then there are, different rounds. Inside the rounds, there is a confusion and diffusion section, which we'll be looking at later. We will look at each round separately. We know that there is a key of 64 bits, which is not directly used. From that, there is permutations and left circular shifts done, and only 56 sub-key, 56-bit sub-key is used in each round. So there are 16 keys, and in each case, the 56-bit sub-key is given to a second permutation, which decreases the size to 48, and 48 is the key size which is given to the round. Okay, so let's look at each of these sections separately. Okay, first, as we saw over here, there is an initial permutation and an inverse initial permutation. Now, please remember this particular point. The initial permutation and the inverse of the initial permutation does not add to the security of the encryption. Instead, when this was being designed, it was being done in hardware, and they needed the data to be input to the hardware in one way or the other. And the easiest way that they found was to hardwire it. And because of that choice, they made a choice of how to input each of the 64 bits. Okay, so that's all. The design required a method for input, and the method that they chose is the initial permutation for the inputting to the rounds, to the DES hardware. Okay, and because the initial permutation is done, obviously, when we are, getting the ciphertext, we do a reverse of that permutation so that we have a similitude of plain text to ciphertext. It does not actually, enhance or decrease from the actual encryption algorithm. Okay, so let's look at what is the initial permutation and what is its inverse. Now, remember, we have 64 bits. Okay, these 64 bits, each bit is rearranged. That is the permutation. All right, so how it is being done? Over here, we have, this is the order. The 58th bit is the first bit in after the initial permutation. 58th, the plain text is from bits 1 to 64. And the 58th bit is given to the first bit. Okay, now we need to remember this initial permutation matrix and the inverse initial permutation matrix. So see how this is done. Over here, 1 is beginning in the last column, and the 5th row has got 1. Okay, so if you see, there are 8 rows. Half of the rows will have the even numbers and the other half will have the odd numbers. So now look over here. This is the first bit. 1, 2, 3, 4, 5, 6, 7, 8. Now 9 again begins in the same way over here. 9, 10, 11, 12, 13, 14, 15, 16. 17 is here. Okay, so we have 17, 18, 19, 20, 21, 22, 23, 24, 25. Okay, till 32 over here. Then 33. 33 to 40 over here, 41. 41 to 48 over here, 49. 49 to 56 over here, 57 to 64 in the last column. Okay, so if you remember this particular order, is very simple to remember what the initial permutation is. Okay, now remember, in the initial permutation, the first bit was replaced with the 58th bit. Okay, so next time over here, wherever the right. Now, in the case of inverse initial permutation, look, the input is this particular, the left hand side and the right hand side is swapped, and this 64 bits is the input over here. So to reverse this, after all these transactions, to reverse the initial permutation, the steps are of that final 64 bits, the first 8 bits are arranged in the second column from bottom row to the topmost row. So we have, and alternate rows is what has got the input over here. So 1 to 8 is in the second row, 9 to 16 is in the fourth row, 17 to 24 is in the sixth row, and 25 to 32 is in the eighth row. Then again, beginning from 1, 33 to 40, 41 to 48, 49 to 56, 57 to 64. This is how the initial permutation, that is this step, initial permutation, and the inverse initial permutation is done. Now we are going to look at the internal structure. Okay. Now for the internal structure, before we go in for what is expansion permutation and permutation function, look at this. This is a single round. See over here, we have seen that there are 16 rounds, and inside this single round, what is happening is what I'm showing you now. Okay, to each round, we have got a 64-bit input, which is divided into 32 bits left-hand side and 32 bits right-hand side. Okay, this right-hand side is given to an expansion or permutation. There is a expansion permutation table. Okay, that I will show you later. Remember, just look at the process over here. The right-hand side, 32 bits, is first expanded. So the 32 bits becomes 48 bits. This 48 bits is XORed with the 48-bit subkey. Okay, and the output is again 48 bits. This 48 bits is then given to the substitution box or the S box. Okay, so this S box is converting 48 bits to 32 bits. Okay, so 6 bytes is converted to 4 bytes. Okay, and then the 32 bits is given to the permutation table, P permutation table, which rearranges those 32 bits, and that output is XORed with the L value, and this L value is being XORed with this particular output. So L value is being encrypted, and we get the R value for the next round. And this R is given exactly like that without any encryption to the next L value. Okay, so in each round, it is the L value that is being encrypted and given to the R. Okay, and the previous R value is directly transmitted without any changes to L. Okay, this is what is happening inside the encryption section. And this section is our key generation section. Okay, we will be looking at the key generation section separately. Now over here, there is the E permutation and the P permutation. Okay, so these two are what I'm showing you now. Okay, so here the expansion permutation, remember expansion permutation means the 32 bits is being expanded to give 48 bits. Okay, so in the 32 bits are going to be arranged inside this over here. See, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, just continuously like that up to 32. This is 30, okay, not 31. This is 30 and 31, 32. Okay, then some bits are going to be twice in our output 48. Okay, so how that is done, this you have to learn by heart. On this side, you have 5, 9, 13, 17, 21, 25, 29, and 01 are repeated. And on this side, 32, 4, 8, 12, 16, 20, 24, and 28 are repeated. Okay, so the 32 bits of the R side, the first bit is there in the normal as well as in the expansion. Okay, then 3 and 0, 2 and 03 are not there twice. 04 you can see is there in the normal as well as on this side. So some bits are repeated twice. Okay, so that is the expansion permutation. So how you get this 48 bits from the 32 bits is shown by that table. Okay, now this permutation is after the encryption has been done using this S box. We're going to discuss separately. Okay, so the output of this S box is a 32 bit, which is rearranged to give the actual 32 bit, which is used for XOR. Okay, so how it is rearranged is being defined by this P table. Okay, so the P function or the permutation function is given over here. This also we have to learn by heart. There is no real order which I can tell you it is in. So you have to learn this. So in this particular order, the 32-bit output after the S box from the S box is given. So the first bit will be the 9th bit over here. Okay, so this permutation is used for the final output. Okay, now other than this, we have got, now we are looking at the S box. Remember that the 32 bits is expanded to 48 bits, and the key is the 56 bits is once again being converted to 48 bits with the permutation, and that is both these values, the expanded value and the K value, is XORed and then given to the substitution boxes or S boxes. Okay, so each input is 6 bits. Remember that this output is 48 bits. Okay, 6 into 48 is, 6 into 8 is 48. So each 6 bits of these 48 bits is given to one S box. And this S box is actually the secret and is the, step by which the encryption is made secure. Okay, now these S boxes are resistant to cryptanalysis. That is why DES is secure. And each of these S boxes has a conversion from 6 bits to 4 bits. How it is done, I will show you. Okay, and then that output is the 32 bits, which is given to the permutation table, and we get the 32-bit output. Now look at the S boxes. This is the secret. How this particular set of values have come, from where it came, all this is not known publicly. Okay, and people have tried over the years to break the code, and they have not been able to break the code. But we have seen that these S boxes, if it is used only once, DES is used only once, then it is susceptible to differential cryptanalysis, and that is why 3 DES is used now. Okay, so we will be looking at double DES and triple DES later, so we can discuss that later. This is the 8 substitution boxes or S boxes. Okay, now the input that we get is a 6-bit input. This is for the key. I will show you the how to get the value. Okay, the 6-bit input that we get, the middle 4 bits, will identify which column should be used. You can see that there are 16, columns, and there are 4 rows. So 2 bits will show which row must be taken, and the middle 4 bits will show which of the column should be taken. Okay, for example, if I have, so 1 second. I'm sharing the white screen here. Say that the input to S1 is 110111. Okay, so it is a 6-bit number. Now these 4 bits, 1011, is going to tell me which is the column that needs to be used. Okay, so 1011, if you convert it into decimal, What is it? 1011 is 11. Okay, so in this case, the output will be the 11th column and 1 is 3, the third row. Okay, the 11th column and the third row. So we will go to S1. Okay, the 11th column is, this is 1, 2, 3, 4, 5, 6, 7. So you start with 0. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay, so we have this column, the 11th column, and the third row. So the value is 9. So 9 depicted in the 4-bit value will be the output. So if my input is 10111, then my output is going to be 1001. Okay, so 6 bits to 4 bits. How exactly these values are given, we do not know. Okay, and to each of these, sorry, this is S5. In S1, I told you we needed. So this is 15, 14, 13, 20, 12, 14. 14 will be the output for the input if the input is given to S1. Similarly, you can see over here, the next 6 bits is given as input over here to S2. The middle 4 bits will designate the column of the S table, and the first value and the second value clubbed together will give you the row. And whatever value is there in that particular position, that is the output that is going to be given as 4 bits over here. In this way, the 48-bit input is converted to 32 bits, and then it is given to the permutation table to give the final output. Okay, so this is the S box. Now let's look at key generation. Now we are looking at the right-hand side. Okay, now let's start over here. Okay, we have a 64-bit key. This 64-bit key, first it is given to the permutation choice 1, and we eliminate some bits, 8 bits, and we get only 56 bits as the output. This is given to a left circular shift, and then the shifted 56 bits is given to a permutation choice 2, and again another 8 bits is eliminated, and we have this 48-bit key given to the each round as Ki of that particular round. So now what we need to do is we need to know how this 64 bits eliminates 8 bits to get 56, how the circular shift is done, and how the permutation choice 2 is done to get the 48 bits. Once this much is done, we have the complete picture of DES algorithm. So now let's look over here. What's happening inside once the 48-bit 56 bits is inputted over here. 56-bit input is divided into 28 bits on the right and on the left, which is depicted by Ci-1 and Di-1. The right-hand side is Di-1 and Ci-1 is the left-hand side. This is shifted, left shift is done in this particular, for this particular bits, and that output is given, this Di value is directly given to Di, and this shifted output is directly given to Ci. And in this particular round of these 56 bits, only 48 is required. So the permutation is going to convert this shifted value to 48 bits and given to the ith round. Okay, so each time the key value is shifted and given to the next round, and the shifted data is permuted to reduce it to 48 bits and given to that round also. Okay, now we will look at permutation choice 1 and permutation choice 2. Okay, supposing this is the input key. So the bits are 64 bits. We write it like this. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. So 64 bits are there. The 64 bits will be written in this particular format. This has to be converted to the 56 bits. Okay, so to the eliminated bits are 8, 16, 24, 32, 40, 48, 56, and 64. These bits are eliminated. And the rest of these bits, the 56 bits, are given to the permutation choice 1. And what is the permutation? The order of the permutation is 1, 2, 3. Okay, this also doesn't have a particular order. So in this particular permutation order, this bit, the first bit, is in the 9th position now. Okay, because the keys will be like this: 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Okay, so this, the order of the bits is from this to this, but the actual key was rearranged in this particular order to get the permutation choice 1. Again, this is a 56-bit output. The 56-bit output is then shifted. How many times? Okay, you can see over here in the first round, the bit is left, the permutation choice 1 is left shifted once and then given to permutation choice 2. In the case of round number 2, it is shifted once. In the case of round 3, 4, 5, 6, 7, 8, it is shifted twice. You should learn this by heart. So in each round, there is a difference in whether the left shifting is done once or twice. Okay, and that shifted value is then permuted to using the PC2 permutation choice 2 table, and this is the 56 bits which is being given to the here. Okay, this left shift is being done. After one left shift, there will be, some values will be lost. And that, see, I will show you here. Okay, this is the permutation choice 1. In each step, we are doing one left shift. So that means these values will no longer be there. Okay, 57. When we do one left shift, one second, 1, 2, 3, 4, 5, 6, 7. It's a 56. It's a 56. Okay. So all these values are permuted, and then from that permutation, only 48 bits, that is the rightmost, these bits will be left out, and the rest of the bits will be given as input to the key. Okay, so just like over here, this section is, left out, this section will be left out, and the rest will be given as the 48-bit input to the round. Okay, now this is how now we have looked at all sections of the DES algorithm. Okay, some of them can be learned by heart, the others cannot be learned by heart, but you need to learn this algorithm in this way itself. All these are fixed values. You cannot change these orders or values. Okay, so you will have to learn it like this itself. Now, another thing that we see is, if we have got the initial permutation, after the initial permutation, we have Li is FA005A00 and Ri is 3CF0, 3C0F. Then, and the key, 48-bit key is given over here like this. Then, after the first round, Li will be, you know that Li is the same value as the Ri. So each time the Li value is simply the previous Ri. Okay, and it is the Ri values that are being encrypted. Okay, and finally, once again, another permutation is done, and you get the inverse permutation is done, and we get the ciphertext. Okay, and this is reversed to get the plain text. Okay, now we are going to see another effect called the avalanche effect. Okay, say that there is, see over here, okay, this is beginning, it's beginning over here. Say that an error occurred, and in the first round, one bit got inversed in R. Okay, during this expansion process and the XOR process, only one error is there. Just like the error is not, doubled when there is expansion process or the XOR process. Okay, but the value which is XORed again with one bit error, if you give this input over here, the one bit error is being somewhere, either it will be in S1 or it will be in S2 or in S3. In any one position, one bit position, there is an error. Okay, say that it is in one of the S's. The permutation inside this S4 causes 2 bits when this conversion is done. Okay, 6 bits are there over here, 4 bits are there as output. When the conversion from 6 bits to 4 bits is done using the S box, the 1 bit error becomes a 2 bit error. Okay, and then there's this permutation step which mixes all these 32 bits. Okay, so the 2 bit error now can be propagated into 2 different positions in the plain text. And then another issue is there, this particular value is being used for the XOR process of the left hand side, and that has already got 2 blocks has got errors. Okay, so in the second round, these 2 bits will be propagated into 2 raised to 2 bits. Okay, in each step, it is going to be, the error is going to be propagated in 2 raised to n steps, in 2 raised to n bits. Okay, and that is called the avalanche effect. So when 16 rounds are over, 2 raised to 16 bits are in error. Okay, are in error, and that is called the avalanche effect. Okay, so we'll just look at the theory. The aim is small change in key or in the plain text produces a very large change in the ciphertext, because in each 16 rounds are there. In each round, the number of errors that is propagated is becoming higher. Okay, so avalanche effect is present in DES, and it is good for security because it causes the error to be obvious. Following examples show the number of bits that change in output when 2 different inputs are used. Okay, so plain text 1 is 02468 ACEECA. So there is only 1 bit, 0000. Here it becomes 0001. 1 bit difference is there between these 2 plain texts. Okay, but the ciphertext for each of these, the difference is 32 bits. Okay, whereas if the change is in key, again only 1 bit difference is there in the key, but the ciphertext difference is 30 bits, and this is called the avalanche effect. Okay, and this is an example with the certain values. The input, the plain text and the key is given over here, and the actual plain text and the changed plain text, error plain text. Here there's 1 bit difference. In the first round, only 1 bit difference is there. In the second round, 5 bit difference is seen. In the third round, 18 bit difference is seen. Fourth round, 34 bit difference is seen. And in that way, 16 bit, when 16 rounds are finished, finally there are 32 bit difference in this particular plain text change. But it began with 1 bit error. But it was propagated, and at the end, when the ciphertext came, 32 bits were different from the actual ciphertext. Okay, and this is called the avalanche effect. For today, I'm stopping now. In the next class, we will look at the key strength. Okay, that is cryptanalysis with DES. Hope you have understood. For any doubts, please feel free to contact me. And don't forget to like and subscribe. Thank you.